How's everyone doing? My name's Colin, and Patrick and I will be going over chapter 45. Why does adding one more bank teller make lines disappear? So, I'm sure at some point in your life, you have waited on a line that simply felt like it was taking forever. And the thing with this chapter is it looks into the theory and the mathematics behind essentially waiting in line and how to minimize that for your customers. So what I'm going to be doing is looking into defining queuing theory for you, while Pat will provide a spreadsheet and some terms that can be used to determine how a customer's time in the system and average number present depend on the number of servers. So first, let's look at the serpentine line. It originated in the 1970s. It was a single line that maximizes utilization of servers, prevents jockeying between servers, and seems fair because everyone is in the same line. So, with queuing theory, there are three factors that determine the performances of a queuing system: number of servers, so quite self explanatory. The more servers you have, the more people that or more customers that they can help out, meaning less wait time for those customers on that line. And then following that is the mean and standard deviation of the time between arrivals. So what that is the average time between arrivals increases, then the number of arrivals decreases. And with that, it increase in standard deviation of intervals actually degrades the performance of the queuing system. And then finally is the mean and standard deviation of the time needed to complete the service. So with that, if the server is going to need more time to actually help the customer and the service that they need, it's going to add on to additional time that the other customers have to wait in that line. So you kind of want to minimize the actual time that the service needs to actually be completed, meaning that people do not have to wait in line as long as they do because services are being completed at a faster or quicker rate. So that's it from my end, and Patrick will be going into the next slide, which is operating characteristics of a queuing system. Thank you.
In the second half of chapter 45, we're looking at the operating characteristics of a queuing system. When looking at the average time spent waiting a line, you must look at these, and line calls for an analysis of the steady state characteristics. In order to carry out an accurate analysis of the queuing system, analysts must have the values of the steady state for the following factors listed below and to the right chart: average time a customer spends in the system, average time a customer spends waiting a line before the customer is served, etc. Once we find out that those values, the fundamental laws of queuing tell us two things. Those are also listed um, below the factors there. The average number of customers present in the system is equal to the average number of arrivals per unit time times the average time a customer spends in the system, as well as the average number of customers waiting in line equal to the average number of arrivals per unit time times the average number of customers waiting in line. Additionally, the steady state theory requires some mathematical assumptions for a few different variables in order to provide a meaningful outcome of the queuing system. The mean and standard deviation of both inter-arrival time and service times change little over time. Technical phrase is distribution of inter-arrival and service times is stationary over time. Also, the number of servers and average number of services that can be completed per unit of time must exceed the average number of arrivals per time, simply implying that you can serve more people than are arriving, thus never backing up the queuing system entirely. The idea of variability is essentially one that throws in the wrench in the plans of this queuing system, in that definitive predictability within the queuing system of service time for each customer is highly unlikely. We see this through the doctor example in the chapter. The doctor example is essentially saying that a doctor sees a patient once every 15 minutes, starting at 8 o'clock. First comes at 8 o'clock, finishes at 8:15. Second one, 8:15, ends at 8:30, and so on. That being said, they then break it up into the doctor seeing half the patients for 5 minutes and half the patients for 25 minutes and see how the variability would affect the queuing system. In doing so, the first patient would come in at 8 o'clock and leave at 8:05. The second patient would come in at 8:15 and leave at 8:40. But with the second patient leaving at 8:40, that means at 8:30, the third patient comes in, thus backing up the queuing system as two people are in the system at one time. Next, we look at the six service example, which is a great example to speak to the real world applicability of the queuing system itself. There are six servers in a store at one time. They perform horribly with 236 average customers in the store at one time for a total of 3,038 seconds in the system, or 51 minutes total. The six servers servicing the mean number of completions per second of 0.01297 equals out to 0.07782. Nearly the 0.07782 customers arrive per second, and 0.07773 customers are serviced per second. The result being a traffic intensity nearing 1 at 0.9989. Clearly, the six servers' capacity are almost being used to their fullest extent. They're operating at maximum capacity and need an additional server to aid their overall performance. As down here to the left, we actually have a chart to speak to this. When adding one chart to make it 7, and then we add 3 more after that to make it 10. As you can see, the slight change of adding one server makes a dramatic difference as the line reduces from 236 to right about 7. But once we see that this dramatic change, there is a law of diminishing returns that comes into play, as adding 3 more actually only cuts down by 1 overall reduction in the total line. Examples speak to the idea that a higher to 1 traffic intensity means a smaller amount of capacity will greatly improve overall system performance. Thanks for listening to our presentation. We're looking forward to the comments in the thread.